Hey, what's up guys? It's Colin, and in today's video we're going to be building circuits of resistors, series, and parallel. And we're going to use simple circuit analysis to find their equivalent resistance. Let's start by building three circuits in series, parallel, and a combination of both. And we'll compare these results. Alright, before we jump into the circuits, these are the parts you'll need if you want to try this out for yourself. Okay, now we're going to start on the resistor circuit in the series format. So what this looks like is going to be basically just a line of resistors. So as the electrons pass through these, each of them has to pass these rough bumps, and so the resistance of a series circuit just add up. And the main concepts you need to understand is that the current, which is the coulombs per second of electrons, is about constant among these, but there's a voltage drop you will experience from each resistor to the other until you reach zero on the other end. And here's the resistance we measured from a multimeter. Now we're moving on to the parallel resistor circuit. This setup is a little bit different, as in the breadboard each line on the horizontal or the vertical axis are all connected, so we're just going to connect them in a line basically. And the main concepts of this one is that the voltage drop is about equal on each side, so it goes from whatever 5 volt input, 0 output on the other side. But the difference is that the current will split among these resistors, with the majority of it going to whatever the lowest resistant resistor is. And we should get a smaller value. And if we look at our multimeter, this is because the lowest resistor takes precedence over the other ones, because it's the resistance is equal to 1 divided by 1 over whatever resistance, and you add the other. We'll get to this into the problem solving section. And lastly, we're going to be working on a combination of the two, the series and the parallel. So this is a more complicated problem you're going to run into. This is going to involve having some of them in series and some in parallel, and you're going to have to break these into steps to actually solve them. So if you look, when we get into the problem solving section, we'll see how we can group certain resistors into series, and then once we find parallels sections, we can group those up. Just remember that you need to look at these by section to solve, and it can be very complicated if you just try looking at the whole picture. So as you can see, this build is a little bit more complicated. This took a little bit of practice to get set up, because when you go from the diagram to what we're actually building, it can be a little bit tricky here. So as you can see, when we measure our resistance, we get 187 ohms, and you can see that our prongs, this is something I set up just with some of the wires I had around, because I do not have alligator clips. And now let's get into the theory section. Okay, now we're going to be solving for the series circuit. So to use our knowledge from before about series circuits, when it comes to resistors, the equivalent resistance is just the addition of them. So what you would do is start by adding them up, just like this. And we should see that our value should be around 800 resistant ohms. If you notice that is a little bit different from what we measured before. And that's because the manufacturers actually list has an error rate of 5%. Also note there's some resistance in the wires, and there could be some in the multimeter itself. But to be honest, this is pretty close, because 40 is 5% of 800. So we actually got less than 5%, it looks like here. Yeah, so our measurement was really accurate this time around. But this is how you find it. Notice that the current that's going through this wire is constant through all of them. So you can use this to find the current. But the voltage is not, because the voltage starts from here, let's say 5 volts, and ends here at 0 volts. And this means it's going to be decreasing as you go from one to the other. If you remember Ohm's law, that the voltage is equal to the resistance times the amperage. So if the amperage is constant, the voltage drops by whatever the provided resistance is in this example. So now we're going to go on to the next problem. So now we're looking at a parallel circuit here. So the big difference in this one is that the voltage is actually constant, because if we go from one point to the other, it goes from 0 to 5 volts. The potential drop always goes to 0 at the end when we get to the other side of like a battery, for example. Now to find this one, it's a little bit harder to find, but if we look at how the current passes through it, we notice that it goes here and then it splits among all these different wires. This is something you'd have to take into account for, because you can't calculate the equivalent current from this. Or you can't from individual ones, I meant. So you know the voltage, and now you need to find the equivalent resistance of this parallel circuit. To do that, you have to start with 1 over, and then you're going to do 1 over again, 150, 1 over 100, plus 1 over 220, plus 1 over 330. So this will give you your equivalent resistance. The reason this happens is because you see that the one of the smallest number actually has the biggest impact, because this is our largest number. And this kind of makes sense, because in this type of setup, the current is going to want to mostly go through the lowest resistance resistor. So it has the biggest impact when it comes to our total resistance here, which makes sense. So to solve this, we should get around like 40, and which just so happens to be around 41. So our numbers are even more accurate here. So we're getting some pretty good resistors. It seems like they're very high quality. I mean, the error rate is labeled as 5%, but we got some pretty accurate numbers here. Now we're going to be moving on to a combination of both. So this is where it can get a little bit more complicated. So to solve these type of problems, we kind of have to break these into small sections using our knowledge of series and parallels. So if you want to start at the right side, we can see that these two resistors are 330 and are 220. They're in series. So we could just like add those together to become one. And once we do that, we should get like a circuit that kind of looks like this, where we have one going this way, one going this way, one going this way. And see how these last two, the 150, becomes in parallel with the previous two? Now we can just combine those by adding it. So we're going to start making our model. We know the last one's in series once we do that. So to find our equivalent capacitance, it's going to equal to 100 ohms plus, and then we're going to do 1 over, and then we're going to get 1 over 150 ohms, and then we're going to get 1 over 330 plus 220 ohms. And this will give us like a pretty accurate number, at least in terms of calculations. But this time around, we should get around 170 ohms from this, which is actually pretty close to what we got from our actual measurements. I think this is a little bit more than 5% off this time around. So yeah, 5% off is actually going to be 178.7. So you can see how it's a little bit more off as we get into more complicated circuit designs. And that should be all. Okay, now let's calculate the amperage of our system here. We know the input voltage is around 5 volts from our battery, and we know the equivalent resistance now. So now we can actually solve it. So we know that the voltage is equal to the resistance. So the resistance times the current equals the voltage. And to find the current, you just divide both sides by resistance. So that's V over R, which is going to be 5 volts over 170.2 ohms, which gets us a current of 0.03 amps as our final result. Now let's calculate the power that's being used. So let's first start by making some space here. So when we're calculating the power, this is how much our thing is consuming and outputting as thermal energy as our device dissipates it. And that makes sense, right? Because when you're using the energy up, like, where's it going? It doesn't disappear. So typically it becomes just heat, it sounds pretty bad because there's nothing you can do with heat. It just kind of dissipates in the air around you. And they calculate that, it's just our volts that we inputted, and then times the amperage that we just found, which gets us around 0.15 watts, which is not a lot. I'd say that's not a lot for a circuit here, but regular computer PCs can be in the hundreds, and that's a lot of energy. So yeah, and that concludes it for today. And thank you for watching my video today. I appreciate you watching to the end, and have a good day.